Here is an error that cost manufacturers millions. Operations teams know their production is low, so they launch facility-wide improvement programs expecting massive returns. They push better housekeeping, run department-wide training, and schedule broad Kaizen events. 6 months later, the overall equipment effectiveness, or OEE, moves barely 3 points. The team is exhausted, and those minor gains evaporate by the next quarter. The problem is that they treated OEE as a single monolithic metric. OEE is actually composed of 3 completely distinct pillars: availability, performance, and quality. Each one has a different cause, a different responsible team, and different required tools. Treating OEE as one giant problem leads to endless cycles of trial and error. Isolating these 3 pillars identifies the primary bottleneck by filtering out the departmental noise. Most manufacturing plants suffer from a dominant loss. This single pillar suppresses overall efficiency more than the other 2 combined. Without data broken out by pillar, departments manage by feel and assign blame. Maintenance blames quality. Quality blames machine breakdowns. Production blames changeovers. Because everyone is partially right, nobody focuses on the primary constraint. This chart breaks down typical loss distributions. When facilities actually measure all 3 pillars, distinct industry patterns emerge. In heavy industries like mining, cement, and metalworking, availability is usually the dominant loss. The sheer cost and frequency of massive equipment failures dwarf all other variables. In high-speed consumer goods like beverages, food packaging, and electronics, performance is the dominant loss. Production bleeds away through silent speed degradation and brief mechanical pauses. In precision manufacturing environments, such as medical devices or automotive components, quality dominates. Sailing to meet first-pass yield dictates the entire schedule. The dominant loss for your industry is generally predictable. However, isolating the specific loss on your particular production line requires hard, segmented data. The improvement strategies we are covering rely on established total productive maintenance frameworks, lean manufacturing principles, and our own deployment of OEE monitoring in industrial facilities. We are going to deconstruct each pillar. For each one, you will get one diagnostic approach and one high-leverage improvement play. The following lessons are designed for immediate application on the factory floor this week. We begin with availability. This formula asks a highly specific question. When you scheduled production, was your equipment physically available to produce? Operating time is your planned time minus all downtime. Operations teams instinctively focus on unplanned downtime. A catastrophic machine failure at 2 p.m. on a Friday commands everyone's attention, but the data consistently reveals a counterintuitive truth. In plants without formal maintenance programs, routine, planned stops like changeovers drain far more availability than mechanical breakdowns. Changeovers bleed time because they lack standardization. Operators clear lines differently, tools are not staged, and new settings are guessed rather than calibrated. What should take 20 minutes takes 45, and the extra 25 minutes vanishes because it is accepted as normal procedure. The precise intervention here is single-minute exchange of die, or SMED, applied directly to your highest frequency SKU changeover. SMED is a formal methodology that forces you to separate internal tasks, actions requiring a stopped machine, from external tasks, which can be prepped while the machine runs. You then strictly standardize the remaining internal steps. Let's get this timeline from a beverage manufacturer. By implementing SMED on a single high-frequency changeover, they compressed the process from 48 minutes down to 19 minutes. On a line executing 4 changeovers per shift, eliminating that unrecorded downtime recovered enough minutes to effectively add a full shift of output per week. The second pillar is performance. This metric calculates whether your equipment operated at its maximum design speed while it was running. 2 primary factors suppress performance: brief mechanical interruptions and deliberate speed reductions. Minor interruptions, commonly called microstops, last under 5 minutes. Because operators quickly clear a jam and restart the line without logging the event, these stops are entirely invisible to human observers. This typographic calculation shows the compounding ding-niche. A machine that pauses for just 90 seconds, 28 times a shift, loses 42 minutes. Across a standard 2-shift operation, That is nearly an hour and a half of pure production capacity destroyed every single day. Alternatively, operators will intentionally run machinery below design speed to prevent those jams entirely. Institutionalizing an 80% run rate treats the symptom while ignoring the mechanical root cause. The diagnostic play for performance is deploying simple inductive proximity sensors on your highest volume line. This feeds cycle times into a real-time system. A garment manufacturer used cycle monitoring and mapped a severe cluster of microstops occurring immediately after break periods. The data proved operators were taking 30 minutes to gradually ramp back up to optimal speed. Implementing a targeted warm-up routine eliminated the lag in 2 weeks. You cannot fix microstops with a clipboard and a stopwatch. Continuous sensor data is the only mechanism that can expose them. The third pillar is quality. This metric is unforgiving because it relies strictly on first-pass yield. Reworked units do not count towards your quality score. Quality failures occur in 2 separate operational phases: startup rejects and steady-state defects. Startup rejects happen during the chaotic transition from stopped to running, usually right after a changeover or a breakdown. Variables are unstable and settings are actively being dialed in. Steady-state defects occur during stable production runs. These are driven by tooling wear, inconsistent raw materials, or operator error over a long duration. You eliminate startup rejects by standardizing your restart process. Document the exact sequence used by your most successful operator and enforce it as a step-by-step checklist to reach process stability immediately. You eliminate steady-state defects by implementing statistical process control. This allows you to monitor leading variables and intervene before a physical defect actually occurs. This split visualization highlights the difference. A concentrated spike of rejected units at startup and a slow drift out of tolerance mid-shift have completely different root causes. Understanding exactly when your defects enter the line dictates which specific tool you need to deploy to stop them. Once you capture accurate data for all 3 pillars independently, your sequence for facility improvement becomes entirely objective. Step 1 is finding your dominant loss on this radar chart. The deepest indentation holds the highest recoverable value. Step 2 requires drilling into the specific loss category. Step 3 isolates the exact machine generating the highest magnitude of that loss. Step 4 applies root cause analysis to that single constraint. Step 5 executes a countermeasure to confirm the OEE increase, moving to the next target. In TPM literature, this is known as Kobetsu Kaizen, or focused improvement. Most plants fail at OEE optimization simply because they jump to countermeasures before isolating the problem. The data always provides the exact coordinates of your constraint. If you lack that granular data, acquiring it is your primary operational objective. There is a critical dynamic that most OEE initiatives overlook. These 3 pillars are deeply interconnected, not isolated vacuums. If you pressure operators to execute faster changeovers to boost your availability score, they often rush the calibration. This introduces a severe spike in startup defects, immediately suppressing your quality score. Similarly, if you force machinery to run at maximum design capacity to boost your performance score, the physical stress creates excessive vibration. Pushing hardware past its stable limit introduces entirely new microstops and dramatically increases your breakdown frequency. Gaining 5 points in availability while simultaneously dropping 6 points in quality is a net negative outcome. You have degraded your overall output while introducing a new mechanical instability. You must monitor all 3 pillars continuously. This ensures you are actually raising the cohesive system rather than just shifting the bottleneck from one department to another. Right now, one specific pillar is suppressing your factory more than the other 2 combined. Broad efficiency campaigns will never uncover it. You now have the framework to segment your data, locate the constraint, and deploy the correct methodology to solve it. Your objective this week is to calculate the availability, performance, and quality scores independently for your most critical production line. Set aside the blended OEE total and find the weakest link. Next week, we map out the exact sequence a real manufacturing site used to push their OEE from 55 to 80% in under 9 months. Subscribe to the channel. 3 pillars, 1 number, 1 direction. Isolating these variables provides the only reliable mathematical path to sustainable gains in total output.